Okay. All right. So, as far as topics are concerned, this exam is going to look a lot like what you've done on the homeworks. And, that includes being able to draw Lewis dot structures without violating the octet rule. It means being able to do VSEPR structures and knowing what the bond angles are supposed to be. You're going to have to do the same style of homework problem on the exam. You need to know the periodic table. Like we said in class today, you won't be given one. Periodic table will be covered. And you're going to have to know periodic trends. So there are going to be some explicit questions about periodic trends. Things like how the radius varies, right? And how the effective nuclear charge varies and how that is related to the ionization energy and the electron affinity of an element. I'm going to ask you some questions about Bent's rule and hybridization and how that is influenced by electronegativity of the elements involved in making the bonds. That's something that was only covered in the online lecture materials that I sent out. So you'll have to watch those. And then the rest of it is going to be point group assignments, symmetry problems and molecular orbital theory. And there's that flow chart in the book that tells you how to figure out which point group each molecule is, but you're not going to have that. And so you're going to have to know the basic elements that define each type of group in order to answer those questions. And then the molecular orbital theory problem, well, it's really sort of a problem in several parts. You're going to have to generate a reducible. You're going to have to break it down into irreducibles. You're going to have to make an orbital interaction diagram and fill it up with electrons. And you're going to have to draw Selks. And that is where it will stop. Okay, so like we've been doing high spin and low spin and delta O and ligand field and all that stuff. That's not on the exam. So it's really just going to be what was covered up to homework, the end of homework 3, essentially. Yeah, except that the pi effects are part of the exam. So you need to know how to do pi effects like pi donor and pi acceptor. What do those do to the energy levels in an MO diagram? And that is about it. So, my experience with the midterm is that people run out of time because the class session is too short to do a proper exam on all that material. And you're gonna have to kind of go quickly on the exam. My experience has been that there are people who really are not prepared to do an MO diagram without any help. Now, the help you do get is you will get a character table. Okay, so you don't have to generate a character table, which is essentially impossible. You'll have a character table and you can work from that to do the MO problem. But being able to go through all of the steps to generate all the irreducibles and then mixing them together and labeling the diagram completely and getting the orbital ordering correct to start with and so on, that's kind of a long sequence of events. And most people figure it out by the time the exam comes around, and some people don't. And if you don't, you're going to do badly. So my number one recommendation to you is to work through all the MO problems on your homeworks and from the notes on your own. meaning like without any help except for a character table, and just see if you can generate a full MO diagram and draw some of the calcs. And then, if you feel like you don't know how to do every single step of that process, then you better figure out what's missing. So the lectures on class maybe will help with some of that stuff. If you're trying to do methane or, tetramethyl titanium in a tetrahedral geometry and you can't quite figure it out, then you can always go back and watch the notes. But I really think you ought to try and do it on your own. So, those are my main pointers, I would say. Know your periodic trends, know your periodic table, and then the rest of it's going to be, your intuition about group theory and how you assign stuff, counting electrons, and so on. So I think it's relatively straightforward. I expect the average to be in the 70s. And so that means that, some people are going to score around 50% or something like that, or less, depending upon how things are really spread out. And some people will nearly ace it. That's kind of how it usually goes. So it's designed to be hard, and it's designed to be full. And that helps me spread the scores out. So I hope it's a good learning experience for you. All right, Pablo, do you want to go ahead and ask a question?
Yeah, you mentioned briefly working through all the problems in homework and lecture for especially molecular orbitals. I was wondering if you had other like practice problems that we should look for, like if there's any in any textbooks that we can go hunting for just to get more like practice with MO diagrams.
Well, I mean, there are examples in the textbook that you could follow, and those things are not perfect, but they're not bad. And you could try and generate your own problems by following the ones in the textbook. So that's an option. Somebody requested that I actually go through the motions on a MO diagram during the review session. So I could try and do another example for you. But aside from that, I don't have a whole lot of advice. Let me see here. Let me see if what I haven't. I'm sorry, I was just searching and searching for my iPad, and I didn't do anything else to prepare for today. Let me just take a quick look and see if I have another example. All right, well, so Esha, do you want to ask a question here before I launch into doing another MO diagram problem?
Yeah, so just on the MO diagrams, is it just going to be one that we have to do for the midterm? Will there be multiple, and will there be d orbitals involved?
You're going to have to do more than one, and I'm not going to tell you exactly what the problem is, but I think you ought to be able to visualize the positions of all the orbitals, what they look like, where they point, and any sort of complex of the type that we've done so far is definitely fair game. You know, I'm not going to the problems we're going to do going forward, the ligands are different from one another. So, or the geometries give you different distinguishable ligand types. like square pyramidal is an example where you've got 4 in a plane and one that's axial. The one that's axial kind of is different than the other 4 that are in the plane, and they sort of operate independently. We're not going to do anything like that. So the problems are everybody's symmetric, so that sort of makes life a little bit easier. Let's see. Okay. So let's do, let me see if I can share my screen. All right, so you guys can see this ChemDraw page, I guess. Is that right? Yeah? Okay, thank you very much.
Yes.
All right, so let's do an example. We're going to do a square planar transition metal compound. I'm sorry, this is not going to be very neat because I'm going to blast through it. But one of my favorite molecules is tetrachloroplatinate. Okay. And so this transition metal complex is planar. Does anybody know what the symmetry group is? Would you say this molecule is polar?
Is it D4H?
It's
Yeah.
D4H. It's D4H because it is flat and flat things like that have a sigma H. Once you know there's a sigma H and that it is symmetric in this way, you can conclude it's D4H. All right. So we're going to call that the y-axis, and we're going to call that the x-axis. And Z is coming out of the paper, right? And that's the principal axis in the molecule. So now, to solve this MO diagram problem, what we need to do is determine which orbitals on the metal and on the ligand combine with each other, right? That's the challenge. Excuse me here. And so what are the orbitals on the platinum center that we're interested in? Well, platinum is in the 5th row. Sorry, the 3rd row. It has 5d as its valence orbitals. It also has 6s, and it also has 6p. Those are all relevant. Okay? These have 0 electrons in them. This guy has 10. Sorry. Okay? So those are your platinum-based orbitals. And the chlorines, what we're going to say is that there are 4 sigma orbitals. Okay? And you could get fancier than that, and you could say, well, the chlorine's got S and it's got P's and so on. But for just doing a sigma only picture, we don't need to worry about that. We're going to treat it like it's a sphere and not get too fancy. Okay? So go ahead, Chase.
Can you clarify how many electrons are in the s orbit, the 6s orbital?
Sure. Yes, go ahead. Ash?
So for this complex, if it's not charged, wouldn't be platinum be +4 and have 6 d electrons?
Well, yeah, what you're saying is reasonable. We're going to just start with atoms. Okay. It does have a charge. This thing has a 2- charge. But I'm not going to be too worried about the electrons at the moment, but let's add that for later. Okay. This guy is 2-. And this compound is platinum 2. And so you're right, it does not have 10, but we're going to start. Our starting complex is just going to be atoms coming together. Okay, so we're going to say that platinum has 10. All right, so the chlorines, we got 4 sigmas. And so now, in order to make the molecular orbital diagram, the next step is to ask, how do we make the irreducible representations, or what are the symmetries of these? Because we need in order to make an MO diagram, we need the symmetries of the orbitals to be the same so that they can have an interaction, right? So how do you do the symmetries of the orbitals in this case? And you know, if you don't know this, this is one of the places where that's got to change, okay? So if you stop and ask yourself honestly, do you know how to generate the symmetries of all these orbitals? I'm going to stop sharing for a second. I want you to see if you can write down the symmetries of those orbitals, all right? And also what you think those orbitals are. You've seen them from my notes, so maybe you wrote it down. See if you can determine those irreducibles. Okay, so I'm gonna tell you the answer now. Now that you've had a chance to think about it. These are the orbitals involved. We've got the 5d, the 6s, and the 6p's. And because the platinum is the central atom, you could just look up the symmetries of these functions on the character table. It tells you. So here's a character table for D4H, okay? And so on the basis of this character table, what would you say is the symmetry of the 6s orbital?
A1G.
It's A1G. It's always A1G. And how do you know that about it?
Because it's symmetrical.
It's a sphere.
Yeah.
Right? And so it's always going to be A1G. It's totally symmetrical. If you were to go through and take a sphere and apply all these operations to a sphere and ask, what do you get back, a +1 or a -1 or whatever, it's always going to be +1 because it's a sphere. And so an s orbital transforms with this symmetry. Okay, that makes it A1G. How about 6px, py, and pz? Well, here, the table tells you the s orbital is not labeled, and that's because it's sort of obvious, okay? But x, y, and z, those are described here in this column of linear functions. So you can go look at the table, and it says pz is A2u symmetry. A pz orbital, if you applied all these operations, would do this. And x and y, px and py, they are in brackets, in parentheses down here. They transform together. A different way to say that is that the X and Y directions are degenerate. They're indistinguishable from one another. The Z direction is distinguishable from X and Y. The Z is perpendicular to the plane of the molecule, but X and Y, you lose track of it. You know, if I flipped you a model of this compound and I said, well, which one of those directions was X and Y, you couldn't distinguish. And that means that they go together, okay? You're always going to get an E set when that's the case. So X and Y, in parentheses, transform as a group. So 6px, py, and pz are A2U and EU. Okay? And how about 5D? You can look at the table and determine. There are all these functions over here that tell you what the d orbitals do, right? There they are. Z squared, x squared minus y squared, xy, xz, and yz. Notice again that xz and yz are in parentheses and the other ones are not, right? So they are A1G, B1G, and EG. Okay? They're the symmetries of the metal-based orbitals. All right, so that's half of the diagram.
Professor, do you
Yes.
also take B2G?
Ah, yes, we need B2G. Thank you. We need B2G because B2G is also a d orbital. So A's and B's are singly degenerate, E's are doubly degenerate. So the sum of these is 5, and there are 5 d orbitals. So we have them all, thanks to Nithme. All right, so there's the symmetries of the d orbitals. Now, we want to go and determine the symmetries of the chlorine 4 sigma orbitals. How do we do that?
Doing the reducible.
And how do we generate a reducible?
Like you see how the CLs move, and if they're like somewhere that's not where they were, that's just 0. And if they stay in the same place, that's 1. And if they're like in another, like in the same place but with different symmetry, that's -1.
The trick where you move the compound according to these symmetry operations and ask whether the orbital of interest, which is namely one of these 4 sigma orbitals, if that orbital moves, it contributes a 0. There is no -1 in this case because these orbitals are not in the center. They're on the periphery. Okay? So this moving business contributes, if they move, you get a 0. All right, so let's just pretend there are 4 spheres here surrounding the center atom. And let's do an E operation. That's the do nothing operation. So the character under this guy, this 4 ligand sigma, is going to be, I'll write it out here. So it's going to be 4. And then under 2C4, where's the C4 operation? Well, it's along the Z. It's the principal rotational axis, right? So it's going to send, excuse me, it's going to send this chlorine here over to this chlorine there. If we rotate it clockwise. And this chlorine here is going to go to that chlorine there. So the molecule spins with the C4. It means that all of them move. Sorry. Let's move this down there. That makes a little bit more sense. All right, how about C2? Now, if you look at the characters here in this character table, those 3 different C2s, and one of them has no prime, one has 1 prime, and one has 2 primes. So which is which? Right? There's a bunch of C2s. One C2 is coincident with the principal axis, and it causes a 180-degree rotation. It's like 2 C4 operations. Notice that the coefficient in front of C4 is a 2. You might imagine that there are really 3 90-degree rotations, but one of them is the same thing as a 180-degree rotation. And so you don't double count it. So this is the principal axis of rotation, but it's a 180-degree manipulation. The primes and the double primes are the perpendicular C2s. One of them goes through the atoms, and one of them goes in between the atoms. Right? This one here, let's make that a dash line. And this one here. Those are C2 double primes. So if we look at the characters underneath those, what is the character under C2? Well, it's the same as the character under C4. 180-degree rotation along the principal axis is going to move all 4 of them. The C2 prime is the one that goes through the chlorine, platinum, chlorine direction. It has 3 atoms on it and 2 that are off of it. So if you spin along this one here, along the x-axis, this one and that one will trade places. They'll move. But these 2 that are on the x-axis won't move. And so the value of the C2 prime is a 2. And the value of the C2 double prime now, so this is a C2 double prime, it swaps these 2 and it swaps these 2. So when you spin about this axis, all 4 of them move. And so the character is a 0. Inversion, since this chlorine to that one, this chlorine to that one, they all invert, so they all move. That's a 0. S4 is easy. It's just a 90-degree rotation. As soon as you've done that, it's over. All 4 have moved. Sigma H. Where's the sigma H? It's in the plane of the paper, right? It's in the board here. The screen is sigma H. And all 4 chlorines are sitting in that plane. Now, the s orbitals are spheres. They're above and below the plane, but they don't move positions. Okay, so the result is a 4. Sigma V's contain atoms. So that's a 2. Sigma D's do not. So that's a 0. Okay, so there's your reducible representation of 4 sigma. By doing this does it move trick. All right. Now, I don't really use that method. Okay. This equation, you could try and break it down and guess. you know, what the A1G, whatever, blah, 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 the various symmetries that make it up. There's some sum of different operations here that make this guy up. So you could start seeing which ones you add together. Another way to do this is to ask, well, can somebody else tell me another way to do this? What do you think another way is?
Did you generate the solve for the 4 sigmas and then looking at the different solves like
So I think what you said, Esha, it was a little bit hard to hear you, but what you said was, can you generate a SALC? Is that right?
Yeah, that's what I said.
Yeah. So if you generate a SALC, what does that mean? You're asking which orbitals on the metal will overlap with which orbitals on the ligand, right? And so if you imagine what the orbitals are doing on the metal, where they point, which ones can possibly make a bond to the ligands?
The x squared minus y squared c squared.
Yeah, there's a couple of them. One is dx squared minus y squared. That's the one that has lobes that are on the xy axis, so they point at all four. Px and py, that's another one that could do it, right? An s orbital could do it. dz squared is another one because it's got a donut, and the donut sits in the plane. So all of those orbitals have the right symmetry. So if I took those ones, A1G is for S, EU is for PX and PY, and B1G is for DX squared minus Y squared, and I added those up, you're going to get this. Oops.
You just add one A1G since it shows up as both z squared and 6s, or do you add it twice?
Well, let's add once. And see what we get. Does A1G plus B1G plus EU equal this gamma 4 sigma? The answer is yes. And you can see that pretty quickly because there are only 4 orbitals in the 4, there's only 4 ligand sigma orbitals to worry about. So the dimension of this reducible is 4. And the dimension of this is also 4. So you can't add any more. That's one way to do it. That's how I do it. So another thing I'll show you, which kind of makes life easy, which is similar. We're going to make some SALCs before we do any group theory. Okay. And I'll show you. It's a nice trick. So when you make SALCs, all right, when you make SALCs for the 4 ligand sigma, and I can tell you what they are before you do any group theory whatsoever. I'm just going to shrink these guys. Okay. The screen has changed sizes on me here. these are the calcs that you can get for 4 spheres in a square. So this is how quantum mechanics works in general. The one on the bottom is kind of like an s orbital in the sense that it's symmetric everywhere. It's the totally symmetric combination of those hydrogen 1s functions. The next highest one has a single node in it. And actually, oh, I've got the nodes misoriented here. Let me fix that. This thing here has one node, and there are 2 of them, and the nodes are just oriented differently by 90 degrees. Okay, and then the top one, there are 2 nodes. You can do this exact same thing for benzene and the pi system of benzene, where you've got 6 p orbitals in a ring, all parallel to each other. The lowest one, lowest energy one, is one where all the p orbitals have the same sign, and you go up and you add 1 node. You flip the node 90 degrees, you do it again. That gives you a doubly degenerate set. And then there are 2 nodes. And then finally, there are 3 nodes where every circle changes sign as you march around the ring. There's this really cool video of a waveform generator that I show in Gen Chem and when I lecture to undergraduates. And it's like a little post.
In this film, we're concerned with the interference.
Yeah, here it is. So this is basically,
knows
pardon
on
me.
any given day, we're all mechanics. DIY.
The music is very dramatic. I don't know. You don't really need to hear it. But basically, there's this plate that's sitting on a little post that vibrates up and down. And the frequency at which it vibrates up and down is controlled by this frequency generator. And all it does is they pour salt on it. And then when they fire the thing up, you get a standing wave in the plate. And if you keep turning up the frequency to higher and higher frequencies, you get different standing wave shapes. And each standing wave shape that you get has more nodes in it. Okay? All of these orbital combinations that we're looking at, where you start from the totally symmetric and then you add a node, you add a node, you add a node, that's just wave mechanics and the types of standing waves that are possible. These are all different harmonics. They're like, when you play an instrument and you play a certain pitch, there's only some pitches that are really resonant with this plate shape. So the same is true in your MOs that you can work with. This is the lowest frequency one, and then this is the next highest frequency, and this is the next highest frequency. Those are the possible combinations. And these things, you probably could guess what their symmetry labels are, right? This guy down here is A1G. This guy here kind of looks like dx squared minus y squared might. And the one in the middle looks like a p orbital. A p orbital has one node. the left side and the right side have opposite sign. Okay, so you can guess what the ligand orbital combinations might look like just if you have a simple symmetric shape like this. Okay? And then you can assign those their point group symmetry if you want. So those are all different ways to go about this problem. The simplest one, I think, is to just visualize the orbitals on the central atom, use the character table to decide what symmetry they have, and then add those up and see if that gives you the right number of orbitals. Sometimes you have orbitals that are non-bonding, though, so that doesn't work completely. And then you have to know what this complete value is and subtract the ones that you can figure out to find out what's remaining. So anyhow, all right, so here's our gamma 4 sigma, A1G, B1G, and EU. And so let's add that to the table.
So is there ever going to be a situation where you would have a reducible representation that you could have multiple irreducibles add up to, and how would you do that?
There are situations where reducible appears more than one time. And you know that there are 4 orbitals to worry about here. And so you can ask whether the orbitals that you've identified reaches the full number or not. And that will tell you whether you found the total number or not. And you might come up short, right? But if you do, then you could turn around and do the move it trick to generate the reducible, the complete reducible, and then subtract the ones that you know are going to be there using this orbital trick if you need to, where you say, all right, which orbitals do I know are going to make a bonds and what are their symmetry? You could just subtract those from the total and then just try and do it by inspection. And if all that fails, you can always use that equation that you were taught. But most of the time, we're going to focus on problems that you can do simply rather than create a bunch of busy work for you on an exam. I would call that a bad exam problem if it turns into a busy work exercise. All right, so we have the symmetries of our components. And honestly, that's most of the game, right? I mean, drawing the lines between the levels, I'm sure you can do that. But let's go ahead and do that. So I think what I'm going to do here is change this document a little bit to make it 2 columns wide. And I can go over here. Very good. All right. So now we're going to make an MO diagram. Remember, this is an energy level diagram. And we're going to start adding some orbital levels. And on the left-hand side, we're going to do platinum. Well, actually, why don't we do platinum in the middle? Because we'll do pi effects next. And we'll do the 4 sigmas on the left, the chlorines. All right, so the 4 ligand sigma orbitals, I'll just draw in 4 lines here real quick. And we know that they are these guys here. And the platinum, we're going to have 5 d orbitals, and they're going to be above the chlorine orbitals. And then in addition, we're going to have p orbitals in the s orbital. There's our p's. Sorry. Ah. There we go. There's our p's and there's our s. Right? And we know that the s orbital is A1G. And what is this guy up here? Do you remember what the PZ is, or the platinum p orbitals? What did we say? A2U and EU. And then the d orbitals we did before. There they are. A1G, B1G, EG, and B2G. And EG. All right, A1G, B1G, B2G, and EG, right? A1G, B1G, EG, B2G. Good. All right, so we've got the symmetries of both, and now we need to make some connections. Now this guy is a little bit, it's pretty straightforward in this case, right? Except that there are two A1Gs on this side and one A1G on that side. So that's going to make life a little bit more interesting. Let's begin by doing that one, okay? Because I think the others are kind of boring. So it'll make our diagram a little bit neater. So let's grab this A1G level, and I'm going to make the all anti-bonding combination up there, and I'm going to make the all bonding combination right there, and I'm going to make the intermediate one fall in between these two levels. So this guy here come on now. This is going to be 1A1G down to the bottom. This is going to be 2A1G, and this is going to be 3A1G. So this is all pretty straightforward. The only tricky part is where do you put the 2? And the 2 I put in between these two A1Gs. So it's bonding with respect to this one, and it's anti-bonding with respect to that one. Right? It's like the anti-bonding combination for this bonding combination, and it's like the bonding combination for that anti-bonding combination. So I stuck it in the middle, which is a reasonable guess. So if you wanted to draw some lines, it would look something like this. There is the 3 A1G symmetry MOs. Okay. All
Do
right.
you also connect to the d orbital since the z or z squared is contributed?
Well, there are 3 A1Gs. There's one here, there's one here, and there's one here. And there are 3 A1G MOs. Here, here, and here. So we've done our job. Okay, all of the A1Gs are represented.
But I mean, you only have lines drawn to the
Oh, crikey.
6S one.
Yeah, you're right. I screwed that up. Let me fix that. Thank you. You are correct. I was thinking, oops, I was thinking about metal on the left side, and that's why I was calmly saying that. When in fact, it should look like this.
So I'm also just curious if the 6s and the 5d A1G orbitals have different contributions, why wouldn't there be a fourth level with like if this level is the S antibonding and the D bonding, why wouldn't there be another level with the D antibonding and S bonding, or is that the same? Is that like also 2A1G?
This gets a little bit complicated, but basically I would say that this is the all antibonding or the most antibonding combination. And this is the most bonding combination. And there's really more than one way to write this out. But this guy is all bonding, this is all antibonding, and this one is kind of in between.
So it's not like strictly one is antibonding and one is bonding, it's just some mixture of the two. We don't
Yeah, it's a
exactly know
linear
what.
combination of the three different A1G components. And you know, the numbers of nodes in the MO that you get that makes up that linear combination goes up as you go toward from 1A1G to 3A1G. So you could try and draw a Salk out that illustrates that. Generally, when we ask you to draw a Salk, what we want is to draw two atomic orbitals, or I guess two atomic-like orbitals interacting. So drawing the Salks of something that's got two orbital components on the metal mixing together is kind of ugly. It's hard to do that well, and so we generally don't do that.
It kind of be like BS hybridization. in this case,
Exactly.
I
There's
guess.
hybridization going on. That's a different way to say this. That's right. All right. So there's the hard one, the A1G. Well, what else is left? We have an EU and we have a B1G. So let's throw in some B1G here. Oops. I'm gonna stick this guy. Right here. No, don't do that. No, well, apparently you can't do that anymore, huh? ChemDraw has disallowed that maneuver. All right, so I'm going to throw in my B1G here. You might ask, how do I know where to put this thing? Okay, so I'm going to put it in this position because I think of this one A1G as being the all bonding combination of three orbitals. So it's like extra bonding. Whereas the B1G is only this one d orbital. But I don't actually know that it's lower. Okay, it could be that the B1 is lower. I mean, I think the A1 is probably lower for the reason that I mentioned. But I'm going to stick it there. The B1G as compared to this guy, well, now that we're lowering the energy of this antibonding orbital because of participation of this A1, I'm going to say, yeah, this thing is lower than the 2B1G for that reason. So when you add in this third orbital, it helps to kind of stabilize everybody. When you're mixing three A1s, everybody kind of comes down. Or at least the 1A1 and the 2A1 come down relative to just a single orbital mixing. Okay? So I'll throw in some lines here. Boom. Boom. And some B1G line there. Boom. And boom. All right. What else is left? Well, we have an EU, and the EU is mixing with these p orbitals up here. They're kind of a long way off, right? So I would say, they're probably not going to be quite as significant because the p orbitals are a long distance away. So I'm going to put the EU combination a little bit higher than these because this platinum p orbitals are further away. There we go. And this guy, where is he going to go? Above the EU set. Is it going to go above the 3A1G? No. Because this guy's got 3 orbitals all in antibonding relationship to one another. All right, so there's your 1 EU. Of course, it's doubly degenerate because it's an E. And there's the 2 EU. Okay. So the interaction's not quite as strong here because we're talking about something that's further away in energy. All right. Let's see here. Did we get everybody? No. What are we missing? So all of these guys are accounted for, but here we have some orbitals that are not part of the picture. There's an A2U, for example. That's non-bonding. And we also have a B2G that's non-bonding. Right? This guy is non-bonding. What is the other one? B2G, right? Yeah. Also non-bonding. The rest of these guys, these ones are definitely sigma stars. Go ahead, Chase.
Wouldn't there also be a non-bonding of EG?
Oh, yes, there's also an EG that's non-bonding. Thank you. So we'll throw in another pairing here. Okay, so 3 of those guys are non-bonding. Why don't we just do it like this? Okay. Now, what do we do with this one? This guy is kind of in the middle here, and we said it's kind of like bonding with respect to that one, and it's anti-bonding with respect to this one. So I'm going to just call this guy approximately non-bonding. Okay. Meanwhile, down here, these guys are all bonding. All right. So there's your diagram. Now, throwing in the electrons is a little bit tricky here, but I'll tell you that the answer is that there are 16 electrons total that fit into this diagram. And so if I put them in here, that would be 8 levels filled. So here's 4, here's 3, and here's 1. This guy right here would be the HOMO of your compound. And that orbital, which orbital is that? Anybody want to take a stab at that?
2A1G.
Yeah, what is that? Give me an orbital parentage, like what type of orbital would you say it is?
D orbital.
A d orbital, that's good. Which type of d orbital would you say it is?
I don't know. I feel like everything is a d orbital sometimes.
Oh man. Well, d orbital's a pretty good guess.
I mean, DZ squared would be A1G, so I would guess that.
Very good. DZ squared is A1G. A1G is Z squared. It's also S. And so this guy is connected to this A1G here and this A1G there. You know this is 6S. And then because this is 6P, this is some 5D orbital. And the A1G is the totally symmetric 5D orbital. That's DZ squared.
So
Okay,
for
so-
the wave function for this orbital, would you say that the S and the D A1G contribute more than, or the S from the platinum contributes more than the chlorine sigma orbitals or S orbitals?
Yes. Well, I would say that
Okay,
it looks
so-
mostly like a D orbital.
But like when writing the wave function, like the coefficient for the 6S A1G and the DZ squared A1G would both be larger than the coefficient for the chlorine A1G.
Well,
in
that's
this case.
definitely going to be true all the way up here for 3A1G, right? And the opposite is true for this A1G down here, which is going to look most like the chlorines. Its
Right, but I
coefficients are
mean
going
for
to be the
2A1G
largest.
specifically.
So the 2A1G is going to be intermediate, but because it is very close to this d orbital level, it's mostly going to look like DZ squared. That coefficient will be the largest. This level here is really like a lone pair on platinum that sits in the DZ squared orbital. The frontier orbitals in this diagram are right here. Those are what we would call the d orbitals on platinum. Okay. So, yeah, go ahead, Chase.
Sorry, my math might be wrong, but I can only count like 16 electrons. And did you say there was 18?
There's 16.
There's like, oh, okay, just.
There's 16. Does anybody want to ask another question about this? Or ask me to repeat some part that went too fast? Or
How do you get
So
to
with-
16?
There are 1 for each chlorine, 10 for platinum, and 2 for the negative charge. You're not going to have to do any funky electron counting, I don't think. But when in doubt, just count the electrons that are contributed by the neutral atom to make the bond. Yes, go ahead.
Could we draw a salx for the DZ squared?
Yes, that's what I would like to do next. Let's do a calc for DZ squared.
So just quickly,
Yeah.
this is just a general question, but I guess I'm just generally used to non-bonding being lower energy than sigma star. So is it possible that the 2 B1G is actually higher in energy than the A1 A2U? Because non-bonding are generally lower in energy.
Well, it's non-bonding with respect to this starting orbital that's quite high in energy. Right? So there's no bonding partner for this 6p orbital. It's possible that this guy, which one is this though? A 2b1g. Yeah, it's possible that this is similar in energy to that one. Just depends upon the strength of the bonding and the magnitude of that splitting. I've never heard anybody suggest that this is higher than that, but I think that's a good guess. All right, so I'm going to draw the calc here for dz squared. This guy is the bonding combination. Okay, so dz squared is in the middle, and then the 4 chlorine sigmas that are around it all have the same shading as the donut. So you could call this one 2A1G. Now, it's not the whole picture because the s orbital is also part of this wave function. We're not going to draw hybrid metal orbitals. So let's just stick with the 2 components that we are interested in for this guy. And it's mostly like dz squared. Maybe you could make these the sigma orbitals a little bit smaller or something. But I'd accept this as your answer.
So how can we deduce from that drawing that it's like approximately non-bonding?
I would say that this drawing does not show you that. And it won't show you that. That's a good question. You would have to know that there's another orbital involved that is lowering this guy. Sorry, this is not, hang on a second. Am I doing this incorrectly? Yes, I'm doing this incorrectly. This is the 1A1G, which is this combination. Thank you. Let's get rid of those. All right. So now this guy, anyway, these ones are out of phase with this donut. Okay. And, if you wanted to get fancy and draw hybrids, you could make one hybrid where the s orbital is dark and shaded or positive, mix it together with this z squared orbital, and it will expand these lobes and it'll cause this one to contract. That's what an s dz squared hybrid looks like. And that would help illustrate that this is approximately non-bonding. There's another version of this where the S is not shaded, but is empty, and it would cause this donut to expand, and that would make the anti-bondingness more apparent. So that's how a calc could illustrate that to you if you were to include the hybridization piece. But you don't need to do that. That's too fancy. Okay. All right. Let's do pi effects. And I'm not going to go through and do this whole thing because I think I want to, it's now 7:20. But let's ask, how do we do pi effects? How many pi orbitals are there?
There's there's 3 d orbitals that could do pi bonding.
On the platinum.
Yeah.
Very good. How about on the chlorine?
The p orbitals.
Of the chlorine? Yeah, and there's really only 2 per chlorine that have the right symmetry to make pi bonds. One of them points at the platinum. That makes a sigma interaction. And the other 2, which are perpendicular to it, those can make pi bonds. So there are 2 pi symmetry lone pairs on each chlorine and or 2 pi symmetry p functions on each chlorine for a total of 8. So we want to find out what 8 ligand pi is. We did 4 ligand sigma. Let's do 8 ligand pi. Okay, and how do we do that?
Do we just not care about the p orbitals?
No, we do care about the p orbitals, but one way you can think about this guy, well, let's solve for the 8 ligand pi for now. And then what we're going to do is add, remember that there's this thing that we did in class. Oh boy, let me see here. Yeah, that's what I want to do. Where we calculated the gamma total, and then we subtract the gamma for the 4 sigma orbitals from it. You remember that? We did it for 12 ligand pi in class, but we're going to do it for the 4 ligands this time. And this thing is the product of, let me get this right. I did the first time. Be smarter than that. Make it a little easier to see here. Right, to determine the 8 ligand pi, we do this thing where we calculate the gamma total, where gamma total, this is not quite right. Let me fix this. There we go. All right, so we've got our 8 pi orbitals that we're interested in knowing about. And we can determine them by calculating gamma total. Gamma total is the product of the 4 sigmas times the XYZ irreducible representation. So this remember, this is kind of like putting an XYZ coordinate system on each of the little of the chlorines. And that XYZ coordinate system you can think about as being a p orbital in all three directions on each chlorine. One of those p orbitals is going to point at the platinum, and it forms a sigma bond. And the other two p orbitals are pi symmetry. Okay? So let's try and draw this out. You remember how we represented this thing as a vector? So there's one p orbital, there's another p orbital, and there's another p orbital. You can think about the p orbitals as being vectors. This one is the sigma-based one, and these two are the pi-based ones. Okay, so if you take gamma XYZ, that's this little XYZ coordinate system, and multiply it by 4 ligand sigma, then you get a representation that looks like a sigma and 2 pi's for each chlorine around this square. And then you subtract the sigma part from that product, gamma total, and you get back the 8 ligand pi. So in our group theory earlier, here's our gamma 4 sigma. Let's do XYZ. All right, so how do we do XYZ? XYZ is on the table. It's actually going to be the sum of A2U and EU. There's Z and there's XY. So this guy is 3, 0, -2, 0. Oh, wait a minute. No, this is the sum, not the product. I'm screwing this up. So it's A2U. This is going to be 1. This is -1. This is -1. This is -1. A2U and EU, right? Yeah. -1 and -2 is -3. -1 and 0 is -1. -1 and 2 is -2. No, it's not. I'm doing multiplication all of a sudden again. Dang it. -1 and -2 is +1. And A2, 1 and 0 is 1. 1 and 0 is 1. All right, so that is the XYZ. So now we're multiplying that by 4 sigma to get gamma total. All right, so this guy is going to be 12. This guy is going to be 0, 0, -2, 0, 0, 0, 4, 2, and 0. Okay? And then if we want to get the 8 pi's, we're going to subtract the sigma from the total. 8, 0, 0, minus 4, 0, 0, 0, 0, 2, and 0. Sorry, 0 and 0. All right, so there's your gamma 8 pi. Okay, so what do? We said, let's multiply gamma xyz times 4 sigma. What do you get? 3 times 4 is 12. 0 times 1 is 0. 0 times anything is 0. 2 times minus 1 is minus 2, and so on. That's the product. This is equivalent to 3 p orbitals on each chlorine. Now, one of those 3 is used to make a sigma interaction, so we can subtract those ones, which is namely this representation right here, and it leaves behind the pi. So that's the pi basis. Now, how do we determine the symmetries of these guys? Well, this is a little bit hard, but one of the tricks that we've decided we can do is the one that Maria used. She said, I know there are 3 d orbitals that have pi symmetry on the metal that match the lone pairs on these chlorines. Okay? They are XZ, YZ, and XY. If you're used to thinking about pi interactions, you can guess that in this problem. And you can go grab them off of the table. So B2G and EG are 2 of the them. That covers 3. What other functions have the right symmetry?
The PZ on the platinum.
PZ and also PX and PY. So the, where did they go? Here they are. A2U and EU. Those are also good. All right, so how many do we have now? 2, 4, 6 out of 8. There's 2 more that are missing. I don't know what they are. I bet that one of them is B1U, and I bet the other one is B2U, but I'm not sure. I would have to do this by inspection, and I'm not going to do that right now. I don't think that's a good use of our time. But I could add these ones up and calculate what that reducible would be, and then we could subtract it from this, and that would leave you behind with some component that's probably made up of B1U and B2U or something like that. Okay, and then you go back and you do it again, and you add your 3 orbitals now. There's the, or sorry, your 12 orbitals now. You've got the 4 sigmas and you've got the 8 pi's, and you look and see what things make connections. We know A2U is going to make connections. We know EU is going to make connections. We know B1G is going to make connections, and we know the E1G or EG is going to make connections, and that's going to modify those. So because these are chlorines and the pi donors, the p orbitals that you make, that you add, are going to be down here. They're going to be at the same level as the sigmas to begin with. Right? So there's these 4, and then there's 8 more. whatever that ended up being. All right, so those are the essential guts of this problem. And it's a lot to do. This is too involved, I think, for an exam. This problem. Maybe not the final, but for the midterm, this is a little too involved to do all these things. Okay?
Are we gonna have to consider pi effects for the midterm?
You have to know about pi effects and pi donors and pi acceptors and how you do this transformation that I just did.
Why are the pi orbitals like the gamma 8 pi lower than the sigma?
It's drawn that way just to help you see that there are 8 that are separated from the 4, but they're really the same starting energy. So maybe I should have drawn it more like this.
Like compared to the diagram that we already drew, should it be lower or at the same?
No, I think it makes sense to draw them at the same energy.
Mm.
They're all kind of like lone pairs donating to the platinum. So they're all the same lone pair, essentially. In the case of the NR2 fragment, and in the case of carbon monoxide, it's much more clear that the sigma and the pi are different. But for a chlorine, I would say they're not really different. All right. What else? Well, let me ask you this. Okay. You know that this orbital, 2 of these orbitals here, they have electrons in them, and they are above these orbitals here. If I add pi effects to these, what's going to happen to them? We know that this B1G and EG orbital interact with the pi's. So what are they going to do? Relative to the sigma only picture, because these guys are above these, they're going to go up like that. Pi donors are going to push the d orbitals up in energy. And if instead this was platinum tetracyanide, and you were asking about the pi stars, now your pi stars are going to be up here, and they're accepting orbitals, and that will drop the d orbitals. And it's easy to remember that if you just think about an electrostatic picture, right? When the orbital is an acceptor orbital, it has an acidity, a kind of a positive charge that lowers the energy of electrons. When the orbital is a donor, it has negative charge. It's basic and electron rich. That will raise the energy of electrons that are interacting with it. Anybody else?
Before you said the thing about the basicity, you said that because some orbitals were higher in energy, we knew it was gonna go up. What orbitals were you referring to?
Well, so this is what it would look like if it was platinum tetrachloride. Okay. If it were platinum tetracyanide, the pi orbitals would be up here because those are pi star on the cyanos.
Mm.
They're empty. And when you make an interaction with these guys, it's going to lower them because these are below those.
Got it.
Matrices. You don't have to do any matrix algebra. Nobody else? Go ahead. Sorry.
So we obviously didn't finish doing the diagram, but if we had to finish, would we have just like added in the pi orbitals into the sigma only picture and then how the sigma changed based on that too?
Yeah, that's right. Yeah. I mean, I guess I could keep going if you would like.
Yeah, can you do a little, just like a little bit more of the diagram?
Sure. Okay, so well, I guess I got to go figure out what these things are. So this sum here B2G, EG, A2U, and EU. So B2G, EG, A2U, and EU. So this sum is 1 plus 2 is 3, plus A2U, and EU is another 3. That's 6, right? So that makes perfectly good sense. E2G and EG again. So -1 and 0 is -1. A2U and E is 1. So this is 0. And B2G and EG is -1. A2U and EU is -1. So this is -2. And B2G and EG is -1. Then B2 or A2U and EU is -1. Did I get that? All right, let me do that again. Sorry. B2G and EG is 1. A2U and EU is -1, so this is 0. B2G and EG is 1. A2U and EU is -1. So this is 0. B2G and EG is 1. And A2U and EU is -1. So this is 0. B2G and EG is -1. A2U and EU is -1. So this is -2. B2G and EG is -1, A2U, that is 1, so this is 0. B2G and EG is -1, A2U and EU is 1, so this is 0. Last but not least, B2G is 1, B2U is -1, so this is 0. So we're going to subtract this to figure out what's left. I'm going to take that out of 8 ligand pi. I'm going to get a 2, a 0, a -2. Sorry, no, a 2. A -4. That's wrong. B2G and EG is -1 and A2U. So this is a -2. -1. -1, good. -1 and -1 is -2. Okay, yes, these are both -2. So then subtracting -2 from -4 is -2. And 0. And 0. And 2. And 0 and 0 and 0. All right, so that's the part we haven't solved yet. And just by inspection, it's a bunch of zeros here. And what did I guess it was? B2U, I sort of liked that one. So A2G and B2U gives you a 0. But it doesn't end that. It gives you a 2. And it gives you a -2. And it gives you a 0, and it gives you a 0, and it gives you a 2, and a 0, and a 0, and a 0. So it's A2G and B2U. Okay? So there is... Sorry, I just threw that spacing off, but... There's our irreducible. So 8 pi is going to be B2G, A2G, EG, A2U, and EU. Let's throw those up over here. Now, we got the first set by asking for, orbitals on the metal where these guys overlap, right? This B2G, EG, A2U, and EU, they're all here. A2U, EU, B2G, and EG. So the other ones, the A2G and B2U one that we just did, those guys are definitely non-bonding. They don't have a partner. So Let's move some stuff out of the way here. Sorry, I just want to give myself a little extra space. All right. So one thing I can do straight away is make a set of A2G and B2G that are non-bonding. Right, these are non-bonding pies. The rest of this diagram is basically going to be the same as it was on this side, except that these pi orbitals are going to raise the energies of anything that has pi symmetry. So for example, these guys are going to go up in energy because this is an EU, and EU appears here. A2U is also going to go up in energy. It appears there. Sorry, that's A1G I got here, but so that's the A2U. It isn't, I got to draw my dashed line. So anything with these p orbitals, they're going up. Because now you're making a bond with these things over here. And the same is true for, so dz squared is not of a 1G symmetry, neither is x squared minus y squared. So I need to move these labels in order to make this work, but I'm going to take these three. I'm going to move them over here. But I'm going to send these up. Okay. And the reason is that they are now pi star. And these guys down here, you're going to get another set that comes from pi bonding with them. That goes down. All right, so there's the non-bonding one. These guys here are EG and B1G. Yikes. And these guys are pi. Right? These are also B1G and EG, but they are now pi star.
I get why the EG goes up, but why does the B1G also go up?
Because have I gotten this labeled incorrectly?
I think it's supposed to be B2G. Yeah. Right.
B2G,
B2G, yeah.
B2G. Oh, there we go.
Yeah,
That's,
yeah.
I just mislabeled it. Thank you. There we are. Right, and which d orbitals are these?
X, Y, Y, Z, and XC.
That's right. Those guys are a pi symmetry. And they are pi star. Here is the pi bonding combination. Okay. Including the pi effects of the p orbitals is also a reasonable thing to do. Generally, you'll just be worried about the d orbitals. But you can add these guys to the mix. There's that label that I lost. Yikes, why do you keep doing that? Right, those are the 5Ds right there. And there some of them went up. These guys are still the same as before. And these ones are going to go up compared to where they were before. So now these labels are going to get more complicated because they are now pi star. And this one is both sigma star and pi star. Of course, all of our A1Gs are in there. Now, do I know if the 2EU goes above the 3A1G? No, I don't know that. Do I know if the B2G goes below the B1G and the A1G? I don't know that. What I do know is that this d orbital is going to get closer to this one, and the ligand field is going to shrink. And my diagram shows that.
So pretty much we don't draw like new orbitals after adding the pi effect unless like something that was like, for example, like the B2GG that it was non-bonding, now it's pi anti-bonding, so we have to draw a corresponding pi bonding. Like we don't add new ones unless something like that happens.
Yeah, that's right. We're only adding orbitals that we have available to contribute, I guess is a way to say it. I mean, to finish this diagram, I would really need to add all these other things. I guess did I start throwing those in? I just got the pi's in here. So I haven't added the sigmas. Did I add the sigmas? I lost track of what I did and didn't do. This is EU, right? Yeah, so this guy's pi. So all of these are going to come down. What did I mark over here? Right. So there's the B2G and the EGs. Those guys came down from interacting with these. And then all of these guys, EU, B1G, A1G. So the B1G is not pi symmetry. The EU is. So the EU comes down, but the B1G and the A1G do not because they're just sigma. Right, so this is EU. Yeah, I'm missing my EU over here. So this EU needs to have a pairing over there that I didn't add. And right, this E1U orbital is now sigma and it's pi. So there's a lot of lines going on here, and it's a complicated diagram. Usually we don't do like full pi effects with S and the p orbitals on the transition metal. You can, you know, but it gets a little bit hairy. Usually what we're interested in knowing is the effect of pi on these Ds. That's kind of what you're going to be asked about.
Got it.
Yeah, so the, you know, the S and the P we include on the diagram because it's helpful to understand the group theory. Typically when we just do sigma pictures, and we can add them to the pi pictures, but after this, we're going to kind of forget about the S's and the P's in our diagrams, and we're just going to focus on the d orbitals. So I don't do this example in class because there's too many lines and too many levels. All right, it's 8 o'clock. I would like to eat dinner. I would like to give you a chance to ask any more pressing questions you might have.
This is very, very brief, but I just wanted to confirm that on the character tables we'll be given, we'll be able to see the linear and geometric functions. So we'll
Yeah.
be able to identify from there where the p and d orbitals are. Okay. I was assuming we weren't going to be given that.
Oh no, that would be,
That would be really bad.
yeah, you could figure it out, but it's not really. For a character table like this, you know, there's a lot of irreducibles. Anybody that's got a lot of representation, a lot of symmetry operations, the character tables get kind of messy. Okay,
Thank you.
you're all set?
Yeah,
Thank you for bringing questions.
Thank
thank
you.
you very much.
All
Thank
right,
you.
gang. I guess I will see you guys later.